Bismillah ar-Rahman ar-Rahim. Last lecture we discussed the decoders, okay, and we said that they are the first functional units that we are going to discuss, okay. And a decoder, basically, a decoder is a combinational circuit that takes in inputs and produces 2 to the n outputs, okay, in inputs and produces 2 to the n output. And the relationship between input and output is that D, which is the output, is equal to the A, which is A, in which A is the input. And from this relationship, we know that the output contains only one or a single bit that is 1, okay, and the rest of the bits are zeros, because basically 2 to the A in binary is going to be 1 followed by A zeros, okay. And then we also discussed the internal structure of a decoder, and we basically showed that this is nothing but a design problem that you guys are capable of doing yourself, okay. And we showed that the decoder, two cases for 2 to 4 decoder and the 3 to 8 decoder, and then we discovered that the decoder is nothing but a min-term generator, okay. It's a combinational circuit that creates all the min-terms, okay. And for this reason, it can be used for constructing Boolean functions, because Boolean functions usually are expressed in canonical form, okay. And canonical forms are either product of sums or sums of product, okay. And we gave an example of how to construct a function using a decoder, okay. But we said that you must connect the most significant bit of the function, which is A in this case, to the most significant bit of the decoder, which is A2 here, okay. So A must be connected to A2, and then the second input, which is B, must be connected to A1, and the third input, which is the least significant bit input, must be connected to A0. Then you take the min-term indices here and take the corresponding decoder output. So D1, D2, D6, because we have min-term number 1 and 2 and 6, okay? And if you OR these together, this is nothing but the sum here, okay? So if you OR these together, you get your function, okay. And we said that if you have many min-terms like this one here we have 5 min-terms, okay. It's not preferable to have a 5 input OR gate, okay. If we have an option, then we want to use a smaller gate, okay. In this case, we can use, instead of sum of min-terms, we can use product of max terms, okay. And this is nothing but taking the other decoder output. Instead of taking 1 to 6, we take 0 and 7, and then NOR them using an OR gate together to construct my function, okay. And we also said that decoders can be used, one decoder can be used to implement several functions, okay. Then we discussed decoders with enable, okay, decoders with enable. And the beauty of these decoders is that they help us in the decoder expansion problem, or in the building of larger decoders using smaller decoders, okay. So, and then we showed how to implement 3 to 8 decoder using 2 to 4 decoders, okay, with an inverter, okay, like this inverter, okay, and 2 to 4 decoders. So this inverter here with this line here is nothing but a 1 to 2 decoder, okay. So basically you used 1 to 2 decoder and 2 units, or 2 quantity of 2 of the 2 to 4 decoders to construct a 3 to 8 decoder. And then we showed another example to construct a 4 to 16 decoder with enable, okay, from 5 counts of 2 to 4 decoders, okay. So now we start our lecture by discussing encoders, okay. Like last time, we said that encoders perform the opposite functionality, okay, as of a decoder, okay. So it takes 2 to n input and produces n output, okay. So for example, we have 2 to 1 or 4 to 2, 8 to 3 or 16 to 4, and etc., okay. Encoders, all right. Okay. So these are some examples of decoders. So in general, we have 2 to n, okay, input, and n output, okay. And the relationship between input and output still holds like the decoder case, okay. So A or D is equal to 2 to A, okay. We don't have to write it in a logarithmic way because usually, typically, only one of the bits of D is allowed to be 1 at any time. If more than one bit is 1, then the output is not guaranteed to be valid, okay. So the output, basically, in this case, if only one bit of the input is 1, the output indicates which bit of D is 1, okay. Like the case of decoders, we can also, if in for the case of encoders, if some input lines are not used, then we can use lesser than 2 to n inputs, okay. For example, if you're using only 12 input lines, you still have four output lines. So it's a 12 to 4 decoders. It's called 12 to 4 decoders. But you're not using the full range of 2 to n, which is 2 to 4 in that case, okay. Yeah, okay. Any question? All right, so now we show the design of 8 to 3 decoder, okay. So the design of an 8 to 3 encoder, I'm sorry. So the specifications is that you have 8 inputs, okay, and 3 outputs, all right. The input is, of course, if you have 8 inputs, then your truth table will contain 256 rows, okay, which is too much. But the beauty of the design here is that the input is only valid when we have exactly one bit that is equal to 1. Okay, so in this case, we only have 8 rows in the truth table. Okay, and they are shown here. There's the formulation here. So this bit here, which is 1, okay, D0 is 1 here. This is the input, by the way. These are the inputs, D0 to D7. Here, D0 is 1, and all the other bits are 0. And this one now moves to the left as we go down in the truth table, okay? Now, if D0 is 1, then we have the output being a 0. So this output here is telling us it is 0, so it's telling us that D0 is 1. This output here corresponds to decimal 2, okay? And it tells us that D2 is 1. This output here, 5, okay? So it tells us that D5 is 1, okay? So each time, the output tells us which input has a 1 in it, okay? So this is how you understand encoders now. All right. Now, for the K-map, if you want to design a K-map for this, how many variables do you need? 8 variables. 8 variables K-map, right? 8 variables K-map is too much, okay? The maximum that we showed previously, okay, was 6 variables came up, but 8 is too much, okay? It means that you have to write down 256 squares, okay, which is too much. So we have to find another way to do that, okay? The other way is that, okay, we just ignore the invalid inputs and assume that these are these are the inputs that we're receiving only, okay? Now, for this, for A2, for example, okay, we have 1 here, okay, which means that if you have 1 here, which means that what? In this row here, the only one is D4, right? So if D4 is 1, my A2 is going to be 1. Or if D5 is 1, then my A2 is going to be 1. Or if D6 is 1, then my A2 is going to be 1. Or if A7 is 1, then my A2 is going to be 1. So my A2 is nothing but the OR of these bits here, okay? My A2 is going to be the ORing of these bits. So D4 ORed with D5, ORed with D6, ORed with D7, right? Okay, what about A1? A1, you just do the same for the corresponding ones in your A1, okay? So A1 is going to be D2 ORed with D3, okay? You can just follow below here as I say it, ORed with D6, ORed with D7, yeah? And A0 is going to be, let me just scroll down a little bit so that you can follow here as I say it, D1 ORed with D3, ORed with D5, ORed with D7, okay? And here you go. This is the symbol, the black box symbol for your encoder. And this is the implementation of your encoder, okay? So we have, we're just showing the implementation using 4 input OR gates, okay? Any question here?
Oh, it's clear.
Okay. If it is clear, then let's move on. Okay, what are the limitations of encoders? First of all, there is a strict requirement that only one input is 1. Exactly, actually, exactly. One input is 1, okay? You cannot even have all zeros, okay? If you have all zeros or more than one input is 1, then you are in big trouble, okay? If you're using just a normal encoder, okay? For example, for the encoder that we showed just here, okay? Let us suppose that D3 and D6 are 1. Just plug in the formulas here, okay? And then you'll notice that A2, A1, A0 are 1, 1, 1. And from this, 1, 1, 1 means what? From the table. What does it mean? It means that D7 is 1.
7, 1.
So what does this mean? It means that our encoder is lying to us, because actually, in fact, it was only D6 and D3 that are 1. Okay? So it is telling us that D7 is 1, but the case is not the case. This is not the case. Okay? So this is one limitation. The other limitation is when you have all zeros. Other limitation is when you have all zeros, okay, you'll get 0, 0, 0. And what is 0, 0, 0? What does it mean? It means that the 0 is 1. Yeah? but I'm having all zeros. I'm not having D0 as 1. Okay, so this is another limitation. Okay, so there is an ambiguity in encoding the input here. Okay, so what is the solution to these problems? The solution is to use what we call priority encoders. Okay, priority encoders, in which we give priority to the inputs. Okay, so we give, for example, higher weight inputs have higher priority than lower weight inputs. So if we have, like this example here, if we have D3 and D6 are 1, then we give D6 higher priority. So our output should be 110 in this case. Okay. The other part of the problem is that priority encoders gives us also what we call valid or invalid output, or valid bit. Okay, so the valid bit will be 1 if the input is valid. The input is not valid, meaning that the input corresponds to all zeros. Okay, then the valid bit will be 0. Okay, so now I'm going to design a 4 to 2 priority encoder. Okay, 4 to 2 priority encoder, and show you how is it constructed. Okay, so the specifications is that you have 4-bit input. Okay, and they are named D3, D2, D1, D0, and then 3-bit output. Okay, including the valid bit A1 and A0. Okay, so let's start with the truth table, or the formulation. The first thing in our truth table. First of all, let me ask you this. How many rows in my truth table?
Four rows.
4 rows, yes.
Only 4 rows?
Maybe 5 because of
I have
the
4
priority.
inputs. 4 inputs.
Yes, 4 rows.
So
Is it 16? Because we are considering every case.
okay, so are you answering with the don't cares in the input? You mean,
Yes.
you mean it's 4 with the don't cares in the input? No, I'm asking you 16. Yeah, it's 16 basically. It's 2 to 4. Okay, 2 to 4 is the number of rows in the input, but we are going to introduce don't cares in the input because there is a priority encoding here. Okay, so don't worry, we are not going to list 16 inputs. Okay, so the first one is going to be all zeros, right? And in this case, this input is my invalid input, right? Invalid input. So for this invalid input, my V is going to be 0. Okay, and this is the only case in which V is 0. Okay, and do I care about A1 and A0 in this case?
No,
Do I care about A1 and A0?
because we have an invalid input, we don't care.
Excellent. It's a don't care. Okay. All right. Now I told you that we should give higher weight inputs more priority. Okay. So now when D0 is 1, okay, in order to have an effect of that, all higher inputs must be zeros. You get that? Yeah. So in this case, what is my output? My output should tell me which bit of the input is 1, right?
Yes, 0, 1.
No.
Or 0, 0.
Okay. اصحوا يا شباب. 0, 0. Okay. And the valid bit is 1. Only invalid input is when you have all zeros. Okay. All right. What is the next one? Next one is going to be I don't care here. Okay. And a 1 here. Why did I put a don't care here? Because basically, if D1 is 1, then I don't care about D0. Okay. But in order for D1 to be of effect, I must have D2 0 and D3 0. Okay. So in this case, my output is going to be valid. Okay. And my A1 and A0 are going to be what?
1 0 0 1.
Yeah, 0 1. All right. Then I have an X here and an X here, and then a 1 here. But this must be 0 for D2 to have an effect. Okay. So this is going to be 1 0, and valid is 1. And finally, we have a 1, and all don't care in the input. Okay. So the output here is going to be 1 1, and the valid bit is 1. Okay. Who can tell me what is the Boolean function for the valid bit V? Even without a K-map, you can immediately figure it out. What is the function that is implemented using, what Boolean operator that V implements?
We get the AND of all these and then invert it. Oh, sorry, we don't invert it.
So the AND, huh?
The OR, sorry.
Yeah. So it is 0 when all the inputs are 0, and 1 otherwise. So it's the OR basically. Or you can say, well, it's max term number 0. Okay. And max term number 0 is basically what? So my V is simply D3 ORed with D2 ORed with D1 ORed with D0. Okay. This will tell me whether the input is valid or not. Okay. And for A1 and A0, you have to have 2 K-maps here. Okay. Okay. For A1, or A1, for example, I have a 1 here, okay, which corresponds to these values. These values correspond to what? To which min terms? Who can tell me which min terms are for these values? It's 4, 5, 6, and 7, right? Because these x's are going to be either 0 or 1. So 4, 5, 6, and 7. Yeah? And these are 4, 5, 6, and 7. They are all ones here. And this one here corresponds to 8, 9, up to 15. Yeah? So the 3 bottom rows, the 3, the 3 bottom rows are all ones here in A1. Okay, and this is nothing but, if this is D3, D2, D1, D0, okay, this is D3, and this is D2, okay? You can see clearly that this is nothing but D3 ORed with D2, right? Yeah? Notice that we assume that the A1 here, okay, which is basically in don't care here, we assume that it is 0. So let me just put it an X here, but we don't take it. We don't take it because if we take it, it will complicate our term. It will complicate our function for A1. It will add more literals to the function, okay? What about A0? A0, let me just, yeah, A0, okay? What is A0? So A0 is going to be a 1 here and here, okay? So 1 here means what? 2 and 3, okay? 2 and 3. And the 1 here means 8 to 15, okay? So this is 2 and 3, all right? And this is 8 to 15, okay? You can see that this is D3 ORed with D1, D2 complement. Do you get it? This is nothing but a revision of K-map. Guys. Do you get it, guys? Any question here?
عندي سؤال.
تفضل.
ما فهمت ليش نستخدم البرايورتي انكودر.
Yeah, so did you understand the limitations of the normal encoder? Did you understand
Yes.
the limit? Yeah, so the priority encoders helps us fix these limitations, okay? So we are giving here, for example, in this scenario here, we want D6 to have higher priority, okay? D6 to have higher priority, and in this case, my output should be 110, okay? And if all the inputs are 0, then we say that the input is not valid. This is the job of the priority encoder. It gives the priorities to inputs so that we don't get wrong output, okay, or misleading output. It also gives us the if the input is valid or not. So this leads us to the implementation of the priority encoder, which is basically has this truth table, okay, and in addition to A1 and A0 as output, we have the valid output as well, okay? You get it, Hassan?
Yes.
Okay. Any question about this? No?
Yes, Doctor.
تفضل.
Does the priority encoder always give higher priority to the most significant bit?
This is the default behavior. If we say priority encoder and we don't specify, then the default is that higher weight inputs have higher priority, okay?
Okay.
But there are priority encoders which do the reverse, okay? But just it's just some other type of priority encoders. Anyway, we will not bother you by this. Just assume whenever it's a priority encoder, assume that the higher priority inputs, higher weight inputs have higher priority, okay? Unless otherwise specified. Okay. So now we have discussed what we call the priority or 2 to 4 priority encoder, okay? And it has how many inputs? I'm sorry, no one corrected me. It's a 4 to 2. How many inputs does it have?
4 inputs.
4 inputs, okay. And how many outputs?
3.
Excellent, yeah. So we just give it like a box here, okay? And then interface it with the outside world. So we have to specify the inputs and the outputs, okay? From inside, okay, you want to use it as a function, as a black box, you have to do that, okay? But you have to show the weights of the inputs and the weights of the outputs, okay? All right, now my question to you, let us say that we have two to four decoder, okay, with A1 and A0, okay, and outputs like D3, D2. Okay. So decoder and encoder, and then this is D3, okay? I connect these together and say, well, this is my X, this is my Y. And I ask you what is V? What is the value of V?
Always 1.
Why is that? It is correct, but you need to tell me why.
Because a decoder cannot give you an invalid output.
Excellent. Yes. So the valid bit is always 1. What about A1 and A0? The output here, I mean.
A1 will be X and A0 will be Y.
Why did you say that? Because we said at the beginning that the decoder, the encoder is, the encoder does the reverse of the decoder. Will anything change if you use a normal encoder, 42 encoder? The only change is that we don't have
A valid bit.
a valid bit. Yeah, excellent. Otherwise, it will stay the same, okay? Because again, the priority, it's true that the encoder has, the normal encoder has some limitations, but the limitations are not the case in this example because the encoder will get its inputs from a decoder, right? Decoder always provides valid encoder input, okay? All right. Let me erase X and Y and erase this and this, and then say, well, this is, I'm going to cross them here. What do you think the output will be? The best way to deal with this is to the truth table, okay? So let's see that this is W and this is Z, okay? And this is, let's say that we call these as D1, or let's call them, yeah, let's call them big D's, okay? D3 and D2. The output is D2 here, okay? And D1, D1 and D0, okay? All right. Now this is D3, D2, D1, D0, and then my W and X, right? So how many rows do I have? Okay, 4 rows only. What is the output of the decoder here?
0001
Yes, and then
0010.
yeah, and then the one goes to the left, yeah,
Yes.
and then 1. Okay, now W and X, calculation of W and X. Okay, which which little d of this encoder is 1 in the first one? D0, right? D0, so my output here is 0, 0. All right? Do you see that?
Yes.
And
Yes,
then,
yes.
and then this one here, okay, is connected to D2. Do you see? This D1 here, D1 is connected to D2. So we have 1 here in D2. How do I? Why did I? Okay, I missed a 0 here and a 0 here. Okay. Yeah, so D1 here is connected to D2 of this encoder. So my encoder here will output what?
1 0.
1 0, which is 2, basically, okay? And then my D2 here, okay, which is 1, is connected where? To D1 of the encoder. So my output of the encoder will be 0, 1. You see that? Finally, my D3 is connected to D3, so no change here. 1, 1. Okay, what is W?
It is basically Y.
Come again?
It is Y. We can
Y.
see from the.
Yeah, from the
It
truth
is
table.
mirrored.
From the truth table, it's same. It's equal to Y, and Z is X. So this is nothing but flipping or exchanging the two variables together. Okay, or switching or swapping X and Y. Okay. So can you do it if we also swap D0 with D3? Will this change anything? I advise you to go back and try that, okay, yourself, and also try other alternatives, okay? One excellent use of this is a BCD to XS3 converter, okay? BCD, which is 8421 to XS3 code converter, okay? So here, my input here is going to be 4, and then we have 16 outputs of the decoder, and then we have XS3, which is which is going to have 4 outputs. So basically, what happens is that you have a decoder here, 4 to 16 decoder, that takes the bits of the BCD. Okay, I'm not going to draw it completely, but you get the idea. Okay, and then we have an encoder here. It doesn't have to be priority encoder. It can be a normal encoder because the output here is always valid, or the input, its input is going to be always valid because of because we are taking it from a decoder. All right. And then we have the 0 here. Okay, when we get a 0 here, I want this encoder to output 3, right? I connect this 0 to D0. This is D0. I connect this D0 to D3 instead. Okay, so I have like 15. And D1, when I have 1, I want my A to be 4. So I connect it to D4. Okay, until I reach what? D, let's say 8 and D9, right? This is the maximum. We're not using the other input, the other outputs of the decoder, okay? Because they are invalid. So this is basically a 4 to 10 decoder, okay? The invalid BCD inputs, okay? So this is going to be 8 plus what? 3, which is 11, right? So this is going to be D11. And then D12, yeah? So this is my going to be BCD. And this is going to be my XS3. Do you see that? So this is a decoder, a 4 to 10 decoder. And this is a actually 10 to 4 encoder. 10 encoder. Right? Do you see the application here? So I used a decoder and encoder to implement a code converter. Okay? Any question?
واضح.
Okay. If you have a question, please ask. Otherwise, let me stop recording, okay?
Doctor, can I attempt to answer the previous task you gave us?
The previous what?
In the previous. Can you
this
go
one?
up a little bit?
Yeah.
Yeah, you told us what would happen if we switch D3 and D0.
Yeah. Okay. Let's do that. Okay. So let's do that. So D3 is going to be connected to. I can use different colors here, for example, just to make sure that. And before that, I will raise this as well. Okay, and so D3 is going to be connected to D0, and D0 is going to be connected to D3. So this is still big D3, and this is still big D0. Okay, yeah. So tell us what happens. Okay, for the middle ones, there is no change, right? It's the same.
Yes.
But for the last ones, what happens?
It will switch the first row and the last row.
Yes. Yes. So this one will be going to be 1 1, and this one will be 0 0. That you're absolutely right. Yes. Because when you get D3, for example, like this here, when you get D3 1, okay, D3 here is going to be feeding D0. So you should get D0 0. Okay. And when you get D1, D0, I'm sorry, D0, like this. Okay. So D0 here is connected to D3. Okay. So you get 1 1. In this case, your W and X are going to be what?
For A1, it will be X invert.
W is going to be X complement. Okay.
Oh,
and
X complement.
and Z is going to be
Y complement.
Y complement. Yes. Excellent. Actually, let's see. Yes, it is. It is Y complement and X complement. Yes, yes. All right. Excellent. Any other question? Okay, let me stop recording.